Hi there, this is Manuel with a new Geometry Nodes tutorial inside of Blender Beta 3.4. Today I want to talk about simulation. You are telling me simulation is impossible inside of Geometry Nodes, and you are right. There is no official way of doing simulation with Geometry Nodes yet, although I think the team is working on it, but there is an unofficial way. And to use this, you have to use a hack. I got aware of this hack when I found a post by Sean Terrell here on Twitter. He created a pretty differential line growth simulation inside of Geometry Nodes, and I was looking at this and asking myself, how did he do it? And by looking at his YouTube tutorial, I got inspired, and I want to use the same buffer technique that he is using to create a simulation inside of Blender. So let's switch to Blender and get started. To do this, what we want to do is we want to create two objects that feed the geometry into each other. And that way we can make use of the way that Geometry Nodes is executed to pass on values from one frame to the next frame. And as soon as we can do that, we can create simulation, because simulation means altering the values based on the values from the previous frame. So how can we approach this? Well, first, select everything and get rid of everything. We will need two objects, and I will just create a plane. Call this plane 0, 1, then Geometry Node, and then Geo. And now I want to duplicate this and call this second object 0, 2 Geometry Nodes buffer, like this. Now let's create a new viewport and switch to Geometry Nodes editor. Go to our Geo object and create a new tree, call it GN initialize. We want to initialize our geometry here. And then we need a second Geometry Nodes tree on our buffer, call this one GN buffer. So with this setup, the geo tree here, the initialize tree, is executed first, and then the buffer tree is executed. So what we can do is we can first create some geometry. Let's put down a sphere, an icosphere. Let's turn this into a volume, mesh to volume, like so, and let's distribute some points inside of this volume. Distribute points in volume. If you don't have this node, please make sure that you use 3.4 beta for this at least. And let's see what this gives, and we get some points. Let's switch this node to use a grid distribution, like so. Now, this is the points that we initially create on frame 1. Now, we want to pass the result of this on to the buffer object. So let's go to the buffer object, cut this connection, and instead drag the geo object into this and connect it to this geometry. So if I make the geo object invisible, you see the geometry is copied over. So now the buffer object stores the results from everything that happens on the geo object. And now back to the geo object, the magic happens by using a switch. So let's lay down a switch node, and a compare node, and a frame node, scene time. And now we want to switch the geometry to the geometry from the buffer object as soon as we reach frame 2. Let's take the switch, and we want to switch whenever the frame is equal to frame 1. If this is the case, we want to create the geometry that we prepared down there. So let's connect this to the true port, and this here. Now, if I press play, the geometry vanishes as soon as I reach frame 2. And now in frame 2, I want to read the result from the buffer object. So let's drag in the buffer and connect it to the false port here. So now let's play, and you see we still have points here. So what happens now is that this geometry is generated, that it is passed on to the buffer, but in frame 2, the results of the buffer are read and are passed on to the geometry of the geo object that then is turned into the buffer object again. And that means now I can do something to my points. I could in theory do this here, but for clarity, I want to create a second Geometry Nodes tree. So let's create a second Geometry Nodes modifier, create a new tree, and call it gn_do. And here I can now do something to my points. Let's put down a set position, something very simple, set position, and let's alter the position of the points. Just by a little offset value, say 0.2. Like so. And now look what happens if I press play. If I press play, you see that everything is moving up. But if you have a close look, you see that you have the geometry 2 times with a little offset between the points. And that shows you what is happening here. So first, we initialize the geometry and pass it on to the next tree. Then the points get moved by 0.2. And everything is moved on to the buffer object, where it is read and fed into the geometry of the buffer. After this, the execution for one frame is over. If I now reach the next frame, I go back to the initialize, but this time the switch just reads the info from the buffer object, so it gets the old information from the previous frame and passes it on to the do tree, which again adds 0.2 to the z coordinate. So this way we created simulation inside of geometries. And if we now make the buffer object invisible, you can see we only have one version of the geometry and we can do simulation inside of geometry nodes. Now let's go to our do tree and create something a little bit more interesting. I want to put down a position field, read the positions of the points and feed them through a noise field. So let's lay down a noise texture, feed the positions in here and sample a noise field. I want to use a color as I'm interested in a noise vector field. But I cannot use the colors directly because they're between 0 and 1 and I want to have vectors that point in all of the directions that are possible. So let's use a map range, switch this to be a vector type, and connect the color here. And let's turn the range 0 to 1 into a range -1 to 1. And now these vectors are probably a little long, so let's lay down a vector math and switch this to multiply. And let's multiply the vector length down to 0.2. And let's connect this to the offset. And something happens here, but probably the noise texture is too complicated. So let's go down to 1 with a scale and let's see what we get here. And you see we get a noise advection. So the points are moving with the noise field. This noise field is filling the entire space with vectors, and the little points are now using these vectors as velocity, so to speak. And they are moving with the field. This is pretty. Let me see if I can make this a little bit more interesting by upping the resolution. So let's go down with the grid resolution to 0.15, say, creating a lot more points. And let's see what they are doing, and all of them are moving with the noise. But you see a problem here. If you are using a Perlin noise vector field, you get a field that does not have a divergence of 0. So you get sinks here. You get areas where all the particles move to and then they are stuck there with these lines. And that is not really pretty, nor is it modeling an incompressible fluid. I think it would be a lot nicer if this would mimic an incompressible fluid flow. And for this to work, the divergence of the field has to be 0. Now we could do a pressure solve step to counteract the divergence as with fluid simulations, but that is of course very complicated. Instead we can use a trick. We could just make use of the fact that if we calculate the curl of the vector field, the curl by definition is divergence free. The curl is another vector field calculated from the original vector field that measures the rotation inside of the field. And we can calculate it, and it will of course be a different vector field, but it will still be noisy and divergence-free at the same time. And as we are using a random-based Perlin noise anyways, it doesn't matter that the curl is looking into different directions. So let's calculate the curl from the Perlin noise to get a divergence-free vector field. But before we start to implement this, let's think about some theory first. So how is the curl defined? Well, the curl of a vector field is defined as a nabla operator across the vector field, and I call my vector field n for noise. That is the definition of the curl. So if you calculate this, this gives a new vector field that encodes the direction of the rotation inside of the field, and the magnitude of the vectors will encode the speed of the rotation. Now, how can you calculate this? Well, the nabla operator is just a vector, a collection of partial derivatives. So it looks like this. It's a vector, and this vector includes the partial with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. That is what the nabla operator does, the vector of partial derivatives. And now you cross this with the noise field. And the noise field has nx, ny, and nz. That is the definition of the noise field. Now, you can come up with a cross product. And this cross product needs the direction vectors. And I want to encode the unit vectors for the 3 directions, x, y, and z, I hat, j hat, and k hat. This is a unit vector in the x direction, the unit vector in the y direction, and the unit vector in the z direction. Now, with all this information, you can come up with a formula for the curl of the noise field. Let me write it down, and then let's think about how to implement this inside of geometry nodes. So to calculate the curl, we want to take the unit vector in the x direction, I hat, and we want to multiply it with the partial derivative of the noise z component with respect to y. And then we want to subtract the partial derivative of the noise y component with respect to z. That is the first operand. And now we want to subtract from this the j unit vector for the y direction times the partial derivative of z, noise z, with respect to x, minus the partial derivative of noise x with respect to z. And then we want to add the unit vector in z direction, k hat, times the partial derivative of noise y with respect to x minus the partial derivative of noise x with respect to y. Like so. So this is a definition of the curl. It's quite a mouthful, and it stems from the definition of the cross product. But what the heck is a partial derivative? Well, if you have a vector-valued function like our noise, say we have two-dimensional noise in this case, so we have a x direction here and a y direction here. This is our input, so just think about a two-dimensional noise field, n of xy. Then we can look at the change of one of the input parameters and see how much it affects the change in the output. So let's define that the output of this function will be the z value. Then we can just draw this. Let me quickly create a new color here to easier see what I'm doing, the red color. So if we take the x and nudge it a little, so we create here an x value and then move it a little. So this will be dx. Then we are interested in the change in z, dz. And if we do this, we are not interested in what happens if y changes. So y is basically constant in this scenario. We are just looking at a little nudge in x, but we can of course do the same thing for the other direction. So we can say, if we take y for example, and we have a little nudge here in y, dy, what does that mean for our z value? Maybe the change is a little less, like here. And now if you make dx and dy smaller and smaller, as soon as they approach 0, you get the partial derivative of these. And you can put all these partials inside of a vector, and this is a gradient of the vector-valued function. But we don't want to use calculus. Instead, we want to calculate these partial derivatives using finite differences. So I intend to do the following. If I have this noise function, and let's stay in 2 dimensions for now, it's easier to understand. What I can do is I can say, let's look at the noise at a certain point. And now let's just take in the x direction, for example, a value of the noise. And now let's add a little notch to this point here, and let's sample our noise value here. We get a certain noise value. And then let's do the same thing for a point that is on the left in the x direction, like so. And we can do 2 different values. And then we just subtract the 2 values, which will give us the change of the noise function around this point in the x direction. And this distance here we will call epsilon. So we will add a little epsilon to our x value and then sample our noise, and then we will subtract a little epsilon from our x value and we will sample our noise, and the 2 values that we get will then be subtracted from each other to create an approximation of the partial derivative in x. And of course we can create the same finite differences approximation for the partial in y and in z, and with these approximations we can calculate the curl noise, or at least we can approximate the curl noise. So with this in mind, let's do this. So we will need 2 things. First, we will need a position. So let's lay down the position node. And we are interested in the components of the position of the points because we want to calculate the partials. So let's lay down a separate xyz, like so. And we will need a value for the epsilon. So let's create a value node and let me quickly rename this to epsilon, like so. And for now I want to pick a value of 0.001. Epsilon should be a very small value. So now let's start with the partial in x. For the partial in x, let's use the math node, math, and let's use the x value from our separate xyz because we are interested in the change in x. So let's first add the epsilon to this value, then let's duplicate this node and let's subtract the epsilon from this value. So now we have 2 samples here, or 2 sampling locations where we can sample our noise. But of course our noise expects 3-dimensional vectors as sample locations. So we want to keep the other 2 components of our position constant. So let's create a combine xyz and let's put this here into x and then the constant y and the constant z in the other 2 ports. Same here, constant y and z in this port. Now we created 2 points around our original position with a little nudge in the plus x and in the minus x direction. Time to sample our noise. But now we have a problem because we want to sample the exactly same noise function twice. And if I create a noise texture, and then duplicate this, this is two different noise functions. I don't want to do that. To be able to use the same noise node more than once, I want to create a group out of it. So just take this noise texture and go to Node and say Make Group. This creates a little noise group here and connects all the inputs. I'm not interested in all of these inputs. I want to be able to specify them from inside of the group. Only the vector should go outside and the outputs, of course. So I just encapsulated my noise inside of this node group. Let's call it noise to sample. Noise to sample. The good thing is, if I now take this node and duplicate it, I created an instance of this node group. So the noise node inside will be exactly the same noise node. This way I can sample the same noise twice. So let's take this noise to sample here and sample the values as I showed you in the theory section. And now I get two values for the partial x. And these two values spit out colors, vectors, so they have three components, x, y, and z, as we had in our formula. Now to make clear what we are doing here, let's take these four nodes and let's add them to a frame. So let's go to Layout Frame and let's put the frame here. Let's take the four nodes and put them into the frame, like so. And I want to give the frame a name. I want to call it x, or let's call it partial x. Well, just call it x, because we have to do the same thing for y and for z. So let's take this, select all the nodes inside and duplicate this and call it y. And then everything again, select everything, duplicate this and call it z, like so. Now for the y direction, we want to do the exactly same thing, but now with the y component. So let's take the y, put a little nudge to it using the epsilon value in both directions, plus and minus, like so. Now let's cut these connections, put the output into the y value of the resulting position, and let's keep the others constant by using the original values from the separate, like so. And now let's do the same thing for the z. Z goes in here, z goes in there, epsilon goes in there, and epsilon goes in there. Now we have to cut these connections, put this in z, and keep everything else constant. X, X, Y, Y. Okay, and now let's sample the noise. 1, 2, 3, and 4. Let's sample the noise at these new locations, like so. And now every noise node outputs the noise at this value. And now we have everything to compute the partial derivatives, or at least the finite differences. To do that, we want to separate the output of the noise fields into its components. So we need another separate x, y, z and connect it to every noise node, because we are always only interested in one aspect of the noise vector output. We only want to use one component of the noise output. So that is why we need all these separate x, y, z's, like so. And now with this in place, we can do the subtractions. We need math nodes now. So let's create a subtract node, math, switch this to subtract, and we need another 6 of these. 1, 2, 3, 4, 5, 6. Because remember, if you look at our formula, we have 6 partial derivatives to compute. 1, 2, 3, 4, 5, 6. And then we have to create 3 subtractions between these partial derivatives. So first we want to create the partial derivative of noise z with respect to y. So noise z with respect to y, this here is respect to y, and here we want to use noise z. So we want to create the finite difference between the z output here and the z output there. Now, next we want to create the partial derivative of noise y with respect to z. That means we want to use the y values that come out of here, respect to z, and we want to create the finite difference between these two values. The next one will be the partial derivative of noise z with respect to x. So noise z with respect to x, this is respect to x, noise z. That will be the first one here and then the second one there. Then the next one is the partial derivative of noise x with respect to z. So that is down there. So x with respect to z. Then we need noise y with respect to x. Noise y with respect to x. That one here. And last but not least, we need noise x with respect to y. Noise x with respect to y. Sorry, that was wrong. This one here. Noise x with respect to y. So now we created the finite differences. And now we want to combine them. We created these partial derivatives as finite differences, and now we want to take the difference between these two, the difference between these two, and the difference between these two. But be careful, this second term has a minus in front. That means we have to switch operands to account for this minus in front. So instead of partial noise e, partial x, minus partial noise x, partial z, we have to switch it around, because this will be minus, this will be plus. So that means here, with our coding, we want to switch out these two components. Like so. And now we can just subtract these. So first we have, remember, partial z, partial y. So that is the first one. Let's just check partial z with respect to y. Exactly. So let's create this one minus this one. And then we want to calculate this one minus this one. Last but not least, we want to calculate this one minus this one. Now we calculated everything according to this formula, and this gives the curl vector. So let's create a combine xyz, and let's put this into the x component as it is multiplied with I. This one is multiplied with j, so y component, and this is k hat, so z component. And now we have our curl vector. But because we used finite differences with a width of 2 epsilon, we have to divide these values by 2 epsilon, of course, to get the correct average between the two positions. So let's use vector math. Vector math, set it to divide. And where's our epsilon at the very beginning? Let's take our epsilon, lay down a math node, math, and multiply it by 2, epsilon times 2, and use this to divide the result. Now this gives the proper average. And now we want to normalize these, because they not only encode the axes of rotation inside of the vector field, but the speed of the rotation too. And I want to use the curl not as a measure of rotation, but instead as a new velocity field, so to speak. So that is why I use another vector math and set this to normalize these vectors. Now with the normalized vectors, I can append a new vector math node, set this one to multiply, and create a value to dial in the speed of the effect, say 0.2 for now. So now I created a curl noise field. I could use it here, but I don't want to. Instead, I want to move it to the do tree. So select everything, copy it, go to the do tree and paste it here. Here we have our curl noise, and now I can use this curl noise to replace this stuff that I did down here. Let's cut this connection, and instead let's use our curl noise. I move this out of the way, and then take all of our curl noise business here, and move this over here. And now I can connect all of this curl noise evaluation to the offset. And I'm very curious on what this gives. And if I now press play, you see stuff is moving around like crazy. So let's go down with the speed to 0.02. A lot better. Got some interesting motion, but it seems to be very intricate. So let's go into our noise here. And let's go down with the scale to 1. A lot better. Now our stuff is moving, and it looks as if we don't get any sinks anymore. Maybe let's reduce the detail to 0 here too, and you see it seems to work. So stuff is moving without any thinking behavior. Okay, that looks promising, but the problem at the moment is that we create the geometry only once. So it is hard to see what exactly is happening. I would love to emit geometry instead of just creating it once. So let's go to our geo object and then to the initialize tree. By the way, we can move all of this out of the way. We just created it here. The actual tree that is executed is up here. And now let's do one trick. We create this geometry here only in the very first frame. And then we read the same geometry again. But what happens if we, after we read the geometry from the buffer object, just join in the same geometry again? Then we would create something that resembles an emission. So let's create a join geometry node. Put it here and just join in the same geometry again. And now let's see what happens. And if we do that, you see now points are created over and over again in every frame, leading to these pretty trails. And now you can perfectly see how these trails start to move through the curl noise field. Now with this emission in place, we are rapidly creating a lot of geometry. So let's go up with the spacing of this grid and let's see what we create here. And you can see now you have it. Now you have this pretty noise behavior where you see that the field that the particles are moving through is clearly divergence free. because you don't get any sink behavior. You don't have areas where all the particles are going to. You don't have areas where the particles are suddenly appearing or disappearing, but this looks as if it is an incompressible fluid. Very pretty. And this is how you calculate curl noise with finite differences and use it inside of geometry nodes to create simulation. I hope this makes sense. If you want to understand the theoretical foundations of this better, I recommend going to Khan Academy. They have a series of some excellent video tutorials on how exactly the curl is working and how to derive all of this. Other than that, I say thank you very much for listening to the tutorial. I hope you learned something, and it is cheers and goodbye. If you like what we are doing, please consider becoming a Patreon. Not only for supporting Entagma, but for access to in-depth courses on topics such as particles, vellum, geometry nodes, and so on and so forth. And at this point, let me say thank you so much to all our existing Patreons. Without you, this channel would not be possible. Thank you.